Welcome back to our statistic learning session. Today we'll be talking about Waltz test. What is Waltz test? Waltz test makes attempt to measure the distance between two vector theta, Emily, and theta naught. To do that, we need to start with the from our last slide where we used where we created some formula to we created some hypothesis where we had something like this, where h naught where h naught is theta mle equal to theta naught, and h1 equal to theta mle not equal to theta naught. Those are two hypotheses, and after some transformations we derived that we had delta uh, we had square root of n I theta mle half theta mle minus theta naught, that that tends to have a distribution of nd in infinity, or in asymptotically, that would have distribution of nd in n dimension of the Gaussian distribution. That's what we got from our last slide. Now, to understand a bit more about the concept and theory, how do we measure distance between this theta mle and theta naught? Now let's take draw a diagram here, and this is theta mle and this is theta naught. Since theta naught is this fixed one, the theta mle is something that is estimated, and it would have something that would vary between those between there would have this kind of range, let's say, on multiple occasions of estimation. And most of the time, the theta mle is equal to theta naught. That's what we want to estimate. That's what we want to prove. And how do we do that? For this, we need the Euclidean distance, or L2 norm distance. That is a square distance between theta hat and theta naught, or theta mle and theta naught. And that's what the Wald used to see how the theta mle and theta naught are close together. Now, at this point, the starting point for our calculation is the statement from our last slide, where square root of n is equal to I, or a Fisher information of theta mle and square root of that, and theta mle minus theta naught, asymptotically equal to normal distribution with the um, with the id that is the that is a what is this, that is that is looks like that looks like identity covariance matrix. There is the identity covariance matrix. Now let's start with some calculation here. Let's start with calculation, where what we want to do is we want to start with the square distance, we want to do the square distance. And now let's start with the distance first. We let's take the L norm first. The first thing is take the L norm of this, that is N I. There are not, and that's why we take the square distance. We take the square. We take the L distance. Now let's just square of this. Next step, we take a square of this. Start N N M L E. Uh, Now we have the square distance of this. This is what we have right now. Now let's try to develop the a little bit more on right hand side of this equation, which is the square of the normal distribution. What we know is that by definition of L2 norm, what do we know this? What do we know about this by definition of L2 norm? But by definition of L2 norm, we understand that if there's an L2 norm vector, that is x, which is x1, x2, and x3, so on, then the distance of L2 norm is x1 square xn square. That's the distance of L2 norm. Now let's take the square of this, and we have square, that is x1 xn square. We have this. Let's take d here. We have this. Now we also know this. The x is a IAD. X at IAD. That is, x has a normal distribution of 0, 1. X has a normal distribution of 0, 1. 0d. The x. This x has a normal distribution of 0d, 0d. That is, x1 has normal distribution of 0, 1. X1, X2, X3 has a normal distribution. Our standard has a standard our standard normals. X1 through XD are standard normals. That's what we know. Our standard normals. That's X1 through XD are standard normals. That is what we know. Next thing we can do is next thing we can do is we can we can say that since this each individual is standard normals, is individual standard normal Gaussians, then we can say that by definition this meets the this has a distribution of chi-square with the degree of freedom d. With a degree of freedom d. Now we can at the same time at the same time at the same time we also know that at the same time we also know that this has a distribution of has a distribution of 0 n 0 normal distribution, so we'll take square of that. Therefore chi-square d distribution is similar to square root of, when you take square root of this, it has similar distribution, is approximately similar. So chi-square d distribution is similar to square root of normal distribution with the variance with the covariance of identity covariance matrix. Now we can go here, we can use this and replace this with this one, which gives us 0 square root n I theta mle square root of that, and theta mle theta naught square, which is tends to xd, that is chi d square. Next step is to look at the left hand side of the equation and see how you can exploit the matrix, how can you exploit the vector multiplication. We know the vector, we know, let's, if the v is a, like now by multiplication rule, let's say vd is a vector of the dimension, and then now let's say multiply this vt by v. So the square root, so the if we square root of this, square root distance of the L2 norm is vt transpose v. Now let's do the same thing here. Let's try to bring this, write that form in, of the transpose format. That is how we can do this. We can do this by we can do this by theta mle theta naught transpose theta mle square root transpose theta mle square root and theta mle theta naught, and which is all we know approximates to chi square. Now let's multiply these two. What we have is n. What we have is, what we get is n, and next step is theta approximate theta mle theta naught transpose should equal to I theta mle, and theta mle theta naught, that should approximately equal to chi square distribution. And this is exactly what we're going to prove here. In the end, what we are just saying is this. What this is what we are saying now. In the end, what we did is we took the chi-square norm and we derived chi-square norm by taking the left side and squared the multivariate Gaussian, and we multiplied the Gaussian, the distance between the theta mle and theta naught, which is distance between those two, and we squared that, which was approximately equal to, which was asymptotically equal to the Theta Gaussian distribution, square of Gaussian distribution, and we derive that square of Gaussian distribution is same as a chi-square distribution, and then we on the left hand side we further refactor and came up with a refined form of the expression, that is n theta mle minus theta naught transpose Fisher information of theta mle multiplied by theta mle minus theta naught, and that's what we got. And this is a Walsh test. Thank you so much. Have a good day.